Hello everyone, this is Jesse Smith from Maryville College, and today I'm going to talk a little bit about related rates. Related rate problems are applications of implicit differentiation. So in order to do these problems, you have to be comfortable with doing implicit differentiation. For almost every related rate problem, we'll have things that are changing over time. We'll denote that by the variable t. So our independent variable will be t, and we'll have other variables which are functions of t, or functions of time. So keep in mind, all of these problems will involve implicit differentiation, and when we take the derivatives, we'll be differentiating with respect to time, or differentiating with respect to t. I'll also give you a word of warning. These are word problems, but you can do these problems, carefully read the problems multiple times if necessary, underline key information, and believe in yourself. You can do it. Here are the instructions for approaching a related rate problem. After you read the question carefully, draw a picture representing the question. Any unknowns or variables that are changing, give them names. It's best to give them variable names that are appropriate. For instance, if you're looking at the height of something, call that variable h. If you're looking at the width of something, call that variable w. Reserve t for time. Again, all of our problems will be changing with respect to time, so reserve the variable t for your independent variable. Write down the numerical information given in the problems in terms of your variables and their derivatives. If you have anything about how something is changing over time, or the rate at which something is changing, that's information about a derivative. Write an equation that relates the variables, and this is why it's called related rates. You're looking for a function that relates the variables that you're interested in. This does require some creativity. You may need to combine two or more equations that relate the two variables, or multiple variables depending on the situation. This part will sometimes require some creativity, some effort, some critical thinking. Just be careful here. Try different things. If you can't find the answer at first, don't give up. Look for other equations, other relationships in the picture that you might be missing. An important word of advice here, do not plug in particular values for changing variables until the final steps. So don't plug any numbers in here. At this point, differentiate both sides of your equation with respect to t. This will be implicit differentiation. Solve for the rate rate you want in terms of what is known. This is where you solve for the derivative or the variable that you're looking for. You'll move everything to the other side, isolate your unknown, the thing that the question is asking for. This is where you do a little bit of algebra. Finally, evaluate. Plug in the variables that you know, the derivatives that you know, the values that you know, and once you do that, you'll actually have your final answer. And be sure to give your derivative if that's what it's asking for. If it's asking for a rate of change, that you give the appropriate units. If it's asking for a rate of change, it will be in some unit per time unit. If it's asking for a height, it'll be a unit like foot or inches. If it's asking for area, it'll be square inches, etc. Alright, so let's work a problem together. In this example, an inverted cone is 20 centimeters tall, has an opening radius of 8 centimeters, and was initially full of water. The water now drains from the cone at the constant rate of 15 cubic centimeters each second. So you can imagine a pinhole at the bottom of the cone, or the tip of the cone, and water is pouring out at a constant rate of 15 cubic centimeters each second. The water's surface level falls as a result. At what rate is the water level falling when the water is halfway down the cone? So the very first thing I'm going to do is to try to draw a picture of this. I'm going to imagine in my mind a cone first of all, water leaving the cone, and then I'm going to do my best to sketch a picture of it. Here's a picture of the cone. I've got a cone, I've got water in it, water is leaving the cone. You can see this arrows indicating for me that the water is going down. I've got water coming out of the cone at a constant rate of 15 cubic centimeters per second. This notation of cubic centimeters per second is giving me an indication that I've got a volume problem I'm looking at. Volume is measured in cubic units, area is measured in square units, distances are measured in single unit distances. So this indicates I'll need to do something with volume. What are the variables in this problem? I've got a cone, I've got water falling, the water's coming out. I don't know the height of the water at any given point. That's changing over time. The amount of water in here is changing over time. If the height's changing, the radius of the top of the water is also changing. So the height of the water is variable over time. The volume of the water is changing over time. And the radius of the top of the water is also changing over time. But what are the constants? What's not changing as time proceeds? The radius of the cone was initially fixed. The height of the original cone was also fixed. It was given to me in the problem. And the rate at which this water is coming out is fixed. That's not changing over time. It has no t in it. It's exactly 15. So let's also give names to these variables. The height of the water, let's naturally call it h. The volume of the water, let me call it capital V. The radius at the top of the water, let me call that little r. It's changing over time. I know this radius of the cone was told to me at the beginning of the problem to be 8 centimeters. The height of the cone was told to be 20 centimeters. And I also know the flow coming out is a constant 15 cubic centimeters per second. Alright, so let's summarize our given information into our picture. The height of the cone is 20 centimeters. The radius of the cone is 8 centimeters. The blue here is my water. At any given random point, the height of the water is denoted by h. This will change over time. Since water is leaving the cone at a rate of 15 cubic centimeters per second, hence the negative, the height will be decreasing over time. Originally it starts out at a height of 20. Eventually it will reach a height of 10, a height of 5, etc. So this is a variable with respect to time. Similarly, r is changing over time. It starts out at 8 at the beginning. It'll be smaller when the height is 10. It'll be even smaller when the height is 5. So r is changing over time, so it's a variable. The rate at which the height is changing is also changing over time. To see this, think about when I first start out, it'll be really slow to see the water drop. The reason is because there's so much volume up here, it will take longer for the water to flow out to make the height drop, because we're leaving at a constant volume. While when we get down here, there's less water that needs to go out of the cone for the height to reduce. So at this point, the height would be dropping faster than originally. By the time I get to the bottom, the height will be dropping even faster because there's even less water volume left in the cone to leave to cause the height to drop. So the dH dt will be changing over time. It'll be really slow at first, and it'll speed up as time goes on. It will of course be negative because the height is decreasing as time goes forwards. The height of the water is decreasing as time moves forwards. I also denote here that I have my dV dt is a negative 15 cubic centimeters per second. Again, it's negative because the water is leaving at a constant rate of 15 cubic centimeters per second. I now want to find an equation that relates the variables. We've been talking about the volume of the water throughout, and we know that the volume of water is decreasing over time and it's leaving at a constant rate. Because of that, I need to look at the volume equation. I'd be looking at the volume of a cone because at any given point, the water filling up part of the cone is itself a cone. If I don't know the formula for the volume of a cone offhand, I would Google it or look it up. The volume for a cone is 1/3 pi r squared h. This relates h, r, and v. I have information about h and v. I really don't have direct information about r. Remember, r was changing over time. And if I differentiated this using implicit differentiation, I'd have to use the product rule, and I would get a problem that involved r and dr dt and dh dt and dv dt. I don't know anything about dr dt. I don't know anything easily or quickly about r. So that seems kind of problematic. So what I'll do instead is look for a way to remove r by another relation. If you look very closely at the problem, there's actually two triangles hiding in plain sight. If you look at the radius of the height of the water at any given point and look at the triangle that it forms with the side of the cone and the perpendicular height, it's setting inside another triangle formed by the original cone with length here of 8, height here of 20. These two triangles are nested inside of one another, meaning that their angles are exactly the same. This angle is the same as this angle in the big triangle. This angle is 90 degrees, that angle is 90 degrees. This angle is the same as that angle. So because of that, we can actually use similar triangles. If you recall from geometry, similar triangles will tell us that the ratio of this distance to this distance is the same as this distance to this distance. So r divided by h is the same as 8 over 20. In fact, the ratio of any two sides of these triangles will equal the corresponding ratio of the sides of the other triangle. So I get that r divided by h is equal to 2/5. So if I solve for r, I get r is 2/5 times h. I can now plug this into the formula for v, simply replacing r by that formula, 2/5 h. Using laws of exponents, I can square this and get 4/25, square this and get h squared. Again, using laws of exponents, I can combine that and get h cubed. Also multiply the fractions out, simplify, I get 4 pi over 75 times h cubed. So I've got a nice formula that relates h and v. I know information about h, I know information about v, and I want to know how h is changing if I know how much v is changing. dv dt is given to me, so if I differentiate this equation, I'll get a formula with a dv dt and a dh dt in it, meaning I can solve for my dh dt. When you're doing one of these problems, you want a formula relating only my givens, or only the givens in the problem, after I differentiate the problem. So if you do the implicit differentiation and you've got extra variables floating around, you need to look for another formula or another relationship to plug into your formula to simplify the problem. So now it's time to do the implicit differentiation. So if I look at v equals 4 pi over 75 h cubed, I take the derivative of both sides. Remember, I'm doing implicit differentiation because v is a function of time, h is a function of time. I'll get dv dt, the derivative of v with respect to time. I can bring this number out in front by the constant multiple rule. Differentiating h cubed, I bring the 3 down in front, reduce the power by 2, leave the inside alone, multiply by the derivative of h with respect to time. This gives me a nice formula that I can simplify a little bit further, canceling the 3 and the 75 to get just a 25 in the denominator. My goal is to find dh dt. The way I can do that is to now use some algebra, divide both sides by this number, and I will solve for dh dt. When you're solving an equation like this, keep these things together. You don't want to multiply both sides by dt to get rid of the denominators. You need to keep this together as its own variable. This together as its own variable. So don't separate your dv dt or your dh dt. Keep the derivatives combined. So if I just think about this as a variable and this is a variable, I can easily solve for dh dt and get dh dt is the following formula. dv dt times 25 over 4 pi h squared. I can now actually put all of my information together and get the final answer. The problem wanted me to figure out DHTT when the water height was at halfway, which in this case is h equal to 10 because the cone was 20 centimeters tall. I also know that dV/dt is a constant -15, so I can plug those two numbers into my equation. This is -15. I know h is. I want to figure out DHTT when h is 10, so I plug 10 in, simplify. It simplifies to -15 over 16 pi. So the water level is decreasing, and that's because of the negative in front. This is also based on our intuition. The water is leaving the cone, so the height of the water should be decreasing. And when we're halfway down the cone, it's decreasing at a rate of approximately 0.2984 centimeters per second. Centimeters per second, because this is measured in centimeters, this is measured in seconds, so centimeters divided by seconds. Some points of advice when you're doing a related rates problems. Take your time reading the question. Read it several times if necessary. You may need to Google or look up a formula if you don't know it or it's not provided in the problem. So if you don't know the volume of a cone, go look it up. If you don't know the volume of a certain shape, go look it up. Sometimes the problem gives you a formula, in which case you know that'll be the formula that you'll be differentiating. But go look for a formula that relates the variables in the question, differentiate it and solve, and keep in mind you can do this. You have to start the problem. Just sitting there with the words in front of you and putting nothing on the paper won't solve the problem. Try sketching the picture. Try naming the variables. Try writing equations that relate the variables. Get a start on the problem and believe in yourself. You can do it. I hope everyone has a great day.